Have you ever looked out of an airplane window during landing and marveled at how gently the plane touches down? The sensation of descending from the sky, the ground rushing up to meet you, and then, almost magically, the wheels make contact with the runway. It seems like magic, a graceful descent from the clouds to the runway. The entire process appears seamless, almost as if the airplane is gliding effortlessly through the air. But behind this seemingly effortless maneuver lies a complex interplay of science, technology, and human skill. Pilots rely on a myriad of instruments and controls, each playing a crucial role in ensuring a safe landing. Landing an airplane is not simply about descending and touching down. It involves precise calculations, constant adjustments, and a deep understanding of aerodynamics. It's a carefully orchestrated dance with the forces of physics, demanding precision and expertise from the pilots at the controls. They must account for variables such as wind speed, air pressure, and the weight of the aircraft. In this exploration of aviation, we'll unravel the secrets of how airplanes land, examining the step-by-step process that pilots follow from the moment they begin their descent to the final touchdown. Delving into the scientific principles, technological advancements, and human factors that make this everyday miracle possible, we'll discover the incredible coordination required between the aircraft systems and the pilot's skills. Fasten your seatbelts as we embark on a journey into the fascinating world of aviation and the art of landing. From the initial approach to the final moments before touchdown, we'll explore the intricacies that ensure every landing is as smooth and safe as possible. To understand how airplanes land, we must first grasp the fundamental principles that govern their flight. These principles are not just crucial for landing, but are essential for every phase of flight, from takeoff to cruising at high altitudes, and finally to the descent and landing. It all boils down to four forces: lift, weight, thrust, and drag. These forces are in a constant state of balance and adjustment, ensuring that the airplane can perform its intended maneuvers safely and efficiently. Lift is the upward force that counteracts the airplane's weight, keeping it aloft. This force is generated by the wings, which are designed with a special shape known as an airfoil. The airfoil shape creates a difference in air pressure on the top and bottom surfaces of the wing, resulting in lift. It's generated by the wing's shape and their angle of attack as they slice through the air. The angle of attack is the angle between the wing and the oncoming air. By adjusting this angle, pilots can control the amount of lift produced. Thrust, produced by the engines, propels the airplane forward, overcoming drag, the air resistance that opposes its motion. Modern jet engines are marvels of engineering, capable of producing immense amounts of thrust to propel large commercial airplanes at high speeds. During takeoff, thrust must exceed drag to accelerate the airplane, and lift must surpass weight to get it off the ground. Pilots carefully monitor engine performance and airspeed to ensure a smooth and safe takeoff. Conversely, for landing, the opposite must occur. The descent phase begins well before the airplane reaches the runway, with pilots gradually reducing thrust and adjusting the airplane's configuration to prepare for landing. Thrust is reduced, allowing drag to slow the airplane down, and lift is gradually decreased until it's just enough to support the plane's weight as it gently touches down. Pilots use a combination of flaps, spoilers, and landing gear to manage the descent rate and ensure a smooth landing. The entire process requires precise control and coordination, making landing one of the most challenging and critical phases of flight. Command. Currently, the VO is 133 words long. Please expand it to be 350 words long. The landing process begins long before the airplane is anywhere near the runway. It starts with the approach, a carefully calculated maneuver that positions the aircraft for its final descent. Air traffic control guides the pilots, providing instructions and clearances to ensure safe separation from other aircraft. The pilots then initiate a descent, gradually reducing altitude and adjusting the airplane's configuration for landing. This involves extending flaps on the wings to increase lift at lower speeds and lowering the landing gear in preparation for touchdown. Throughout this phase, pilots constantly monitor their instruments, making precise adjustments to maintain the correct speed altitude, and heading for a stable approach. Section 4. The final approach. Precision and skill in perfect harmony. As the airplane nears the runway, it enters the final approach phase, the most critical stage of the landing process. Here, precision is paramount. The pilots must maintain a steady descent rate and align the airplane perfectly with the runway center line. They rely on visual cues from the runway environment, such as the runway markings and approach lights, as well as their instruments to guide them. This delicate dance between human perception and technological aids demands a high level of skill and experience, especially in challenging weather conditions, where visibility is reduced. Section 5. Instrument Landing Systems, ILS. Guiding lights through the clouds. In situations where visibility is poor due to fog, rain, or snow, pilots rely on instrument landing systems, ILS, to guide them safely to the runway. These systems are essential for maintaining safety and precision during landing approaches when visual cues are minimal or completely absent. The ILS technology has revolutionized aviation by providing a reliable method for pilots to land aircraft in conditions that would otherwise be deemed too dangerous. ILS is a ground-based navigation system that provides pilots with vertical and lateral guidance during the approach and landing. This system is composed of multiple components that work together seamlessly to ensure that the aircraft follows the correct path to the runway. The precision of ILS allows for landings in low visibility conditions, significantly reducing the risk of accidents and improving overall flight safety. It consists of two beams: the localizer, which provides horizontal guidance, ensuring the airplane stays aligned with the runway centerline. The localizer beam is transmitted from the end of the runway and extends outward, creating an invisible path that the aircraft can follow. This horizontal guidance is crucial for maintaining the correct alignment with the runway, especially when visual references are not available. And the glide slope, which provides vertical guidance, helping pilots maintain the correct descent angle. The glide slope beam is transmitted from a location near the runway threshold and projects upward at a specific angle, typically around 3 degrees. This vertical guidance ensures that the aircraft descends at the proper rate, avoiding obstacles and ensuring a smooth touchdown on the runway. Pilots monitor the ILS signals on their instruments, making adjustments as needed to stay on course. The cockpit displays show the position of the aircraft relative to the localizer and glide slope beams, allowing pilots to make precise corrections. This constant monitoring and adjustment are vital for maintaining the correct approach path, especially in challenging weather conditions. The ILS is a crucial tool for ensuring safe landings in adverse weather conditions, allowing airplanes to land even when the runway is not visible to the pilots. By providing both horizontal and vertical guidance, the ILS system enables pilots to execute landings with a high degree of accuracy and safety. This technology has become an indispensable part of modern aviation, ensuring that flights can operate reliably and safely, regardless of the weather conditions. Section 6. Autopilots and Autoland, the rise of automated landings. While pilots are ultimately responsible for landing the airplane, they have increasingly sophisticated automation systems at their disposal to assist them. Autopilots, for instance, can maintain the airplane's altitude, speed, and heading, reducing pilot workload, especially during long flights. Some modern aircraft are equipped with auto-land systems which can take over the entire landing process from the final approach to touchdown. These systems use a combination of sensors, computers, and actuators to control the airplane's flight path, making precise adjustments to maintain the correct glide path and land safely on the runway. While auto-land systems represent a significant technological achievement, they are typically used only in specific conditions, such as low visibility, where they can enhance safety.